Sometimes, though, when we observe data in real life, not all data will follow a perfect linear relationship and form a perfectly straight line. Sometimes it'll represent something that's very close to a straight line and have a very strong correlation, but won't actually be a straight line. So when we find that, what we do is we find an approximation of a straight line, which we call the line of best fit. To have a look at the line of best fit, we're going to have a look at an example of a real life scenario of a cricket match. So if we have a look at, before we go through the cricket match, a line of best fit, it goes through as many points as possible. So we wanted to get as many of as much of the information on the line as we can. Won't always happen, but we want to try to. Again, ideally would have half the points above and half points below, and is drawn so that the distance from the line to each point is as small as possible. Now, this is in an ideal world we'd have that. It's not going to happen in every single situation. Let's look at it in relation to this example. A cricket team's progressive score during 50 over match is shown, and here we can have at varying different points without the match their different score. Now, we can see this does not follow a perfect linear relationship. It's close, but it doesn't. So what we're going to do, we're going to graph this and construct a line of best fit, so we get an approximation of a straight line. So first of all, I drew up a set of axes, and on my y-axis have my runs, which is my dependent variable, and on my x-axis have my overs, which were my independent variable. Now in a match, nothing is going to change the overs. We have to bowl 50 overs no matter what. How many runs you score depends on how many overs you bat for. So that's why we have a dependent and independent. As you can see as well, along the graph, I've plotted bits and pieces of information. What I need to do now is construct a line of best fit. So I need to go have a line, use my ruler. Ideally a see-through ruler is the best for this. We want to make sure that when we place our ruler on the page, because it's a cricket match, at the start of the match you start on 0 runs, and we want to try and get as many of these points as possible involved in the line. And if we can't get them involved in the line, we want to get them as close to the line as possible. So you maneuver your ruler around until you get as close as you can. You're not going to get exactly there, you're going to get pretty close, but you won't get exactly there. So I'm going to use, hang on, I might just move that a bit. So I'm fairly close there, and I'm just going to draw my line up through there. Now when it comes to a HSC, not everyone's going to have their lines constructed exactly the same. So they're going to allow a range. So what we can see here, I have my line passing through 1 and 2 points. We know that these 2 points are definitely involved because at the very start of the match you've scored no runs. And then up here I've crossed the line through this point. Here we can see I've got 1, 2, 3 dots above it, 2 dots below it. So again, I've roughly got half the scores above and half the scores below. And here you can see I've tried to keep the distance between the line and the dots as small as possible. So there I've constructed my line of best fit. Plot the points on your graph, get a see-through ruler, and get as close to as many of the points as you can. Now that we've done that, we'll go through and answer the rest of the questions. Question B asks us to find the equation of this line. First off, from last video, and we know that to find the equation of a line, the equation of the line is in the form of y equals mx plus b. In this situation, my x is represented by O for overs, and my y is represented by R for runs. So my formula needs to be something along these lines. First step, we always find our gradient. I'm going to pick 2 points on the graph. I'm going to pick this point because I know at the start of the match they scored no runs, so it's 0-0. and I'm going to look for a point on my graph where the line meets exactly with the corner of a box. So I'm going to pick there, and what I'm going to do to make my life easier, I'm just going to put some dotted lines in so I can see where that data exactly falls. And what you can see is that there's a triangle being made, and that's what we get when we pick out 2 points. So that's my points, and that is at over 25, halfway between 20 and 30, and 121 runs. So that's at point 25, 120. Well, looking at my 2 points, my change in rise, so from 0 to 120, my change in rise is 120, and my change in run from 0 to 25 is 25. 120 divided by 25, do that on your calculator, and you'll get 4.8. So 4.8 is our gradient. So far our formula now looks, we have R equals 4.8 O plus B. Well, let's have a look. Remember, our B is where our line crosses the y-intercept. If we have a look at our y-intercept over here, you can see the line crosses through at 0. So our B is going to be 0. Since it's 0, we don't write it. So our equation of the line is R equals 4.8 O. So runs equals 4.8 times O. So there we have the equation of our line. Question C asks us to use our equation to estimate the score at 50 overs. So runs equals 4.8 times, and we want to know what the score is at the end of the 50th over. So we substitute 50 in there. 4.8 times 50 is 240 runs. So using our equation, we can estimate that they're going to be around 240 runs. D. Question D asks us, using the line, so using this line that we've created, estimate in which over the team score reached 100. To do that, just draw straight across from the 100 runs till you meet your line. Once you get to your line, draw at a right angle straight down to your overs, and here we can see it's around the 20th over, so we can say approximately 20th over is when the team reached 100 runs. Question E asks us, a cricket team's run rate is the average number of runs per over. What was this team's run rate? Well, a run rate is like an average. It's what you're constantly changing by. Remember, our gradient is an indication of constant of change. So here, when they ask us what the team's run rate is, they're asking us to write down what is their constant of change. So we have 4.8 runs per over. That's their constant of change. It's what our gradient is. Question F asks us, what are the limitations of this model? So what are the problems with a line of best fit? A line of best fit is only an approximation of the data. Here we can see it only uses some of the data points. It doesn't take into consideration everything. If we actually look at this team, we can see that in the last couple overs, they started to stray off. They started to score less runs than our actual model predicts. There's a big gap between these 2 points here, we can see. That's a limitation of the model because it's only an approximation. So it's only an approximation of data. So quickly, just running through it again. A line of best fit, once we've graphed or once we've plotted all our individual data points on a table on our axes, our line goes through as many points as possible, has roughly the remaining points above and below it, so separate them as much as possible, and is drawn so that the distance between the dots in the line is as close as possible.